First, we will talk about the introduction. So, direct current DC motor drive is a type of an amplifier or power modulator that functions by integrates between the controller and DC motor. The process takes up a low current present and convert it into a one of high current which is suffice for the motor. In addition, the DC motor also provides the high current torque exceed than that of the rated continuous torque. The importance of DC motor application that provide a reliable drive system has been widely practiced within the industry. Such the important way to achieve this is by deploying H-bridge converter. For DC motor, the characteristic that has been provided by the H-bridge is speed-torque characteristic, where this characteristic will operate motor in forward and backward direction in the all four quadrant operational. To provide protection and the isolation of the H-bridge circuit is designed. In order to relatively operate the motor, proportional integrated derivative controller (PID) with pulse width modulation (PWM) full bridge DC-DC converter were used. As for this assignment given, a design of torque controller and speed controller was proposed. This controller is used in order to determine the parameter of PID for tuning method. The motor parameters and ratings is set up by the following commercial available DC motor that were chosen with two different power level, which is a low power DC motor at less than 500 watt power rating and a medium power level DC motor between 1 kilowatt to 5 kilowatt. The overall system was constructed by using a MATLAB simulating software, presenting the different methods of operation and further discussed. The design of the speed controller and torque controller for the closed-loop DC motor for quadrant operation has been shown to be effective at near reference level. The objective of this project is first to design and determine the parameters of the DC motor drive system based on the two levels of power rating that were chosen, which is a low and a medium power rating. 2. To model the cascade control structure for controlling the speed as well as the torque of the DC motor by using a MATLAB simulating software. 3. To determine the PI controller values for both the torque and the speed control loop and conduct the performance analysis of the controllers by using the board plot. And the last is to verify the performance of the DC motor drive system through the MATLAB simulation in all four quadrant operation. As for methodology, the purpose of this assignment is to design and determine a suitable controller which are able to control both the speed and torque of a permanent magnet DC motor, thus fulfilling all four quadrants operational of the motor. First, we'll start with choosing a suitable motor design according a suitable specification datasheet that is available. The motor used for the design is chosen from a commercially released product from an online catalog, and we use baldo.com. As such, the specs were reliable. The project is designed and simulated using MATLAB simulating software to test the accuracy of the speed and torque of the motor, which is cascade controller, speed and torque controller. The performance result will later be observed and evaluated in terms of their speed, torque, and its armature current. These are the details of the motor that are obtained from the catalog ABB Motors and Mechanical website, which is baldo.com. As such, the type of motor used is the CDP3330 V90 for a low DC motor and a CDP3580 V180 that were chosen for a mid-power level DC motor.
A cascade control structure is a controller that were put in array together to form a simultaneous control of a system. For example, a motor. This motor was controlled by using a bunch of PI controller, that is speed PI controller and torque PI controller. Speed PI controller controls the speed of the motor so that the motor stays at its rated speed. The speed PI controller inputs the current speed of the motor and output torque. This occurs by an algorithm by the PI controller that compares the current speed of the motor and the rated speed. The torque PI controller inputs torque and outputs torque that were calculated by the torque PI controller, and the switching mode converter receives the signal from the torque PI controller and regulates the torque needed by the motor. The current torque of the motor were obtained by the current IA with the constant Kt. Therefore, a cascade control structure is basically a loop of control systems that were limited by its reference value. This is an example of a torque control loop that were transferred into a MATLAB simulation. It is basically a cascaded equation of a PI torque converter and DC motor that were multiplied together to form an equation. Then we convert it to MATLAB block by using the equation. This is example of PI controller speed control loop. The speed control loop is basically also from an equation of a speed PI controller that were converted to PI control loop, speed control loop, in form of MATLAB blocks. The speed control loop consists of speed PI controller and torque control loop combined with the DC motor. This is a complete model of a torque control loop that were cascaded together with a permanent net DC motor. The system is controlled by an outer speed control loop that were connected with other input signal to control the motor quadrant. This is a cascade control structure that has been modeled by me in a MATLAB blocks. As we can see, the input of the cascade control structure is from a step and output a signal to kind of a signal that were inverted. The signal's purpose is to control the switching of the motor, therefore can control the quadrant of the motor. To control the quadrant of the motor, the step were plotted at different values. Therefore, by adjusting the step values, we can control the quadrant of the motor. Here is the full view of a cascaded control structure controlled by a PI controller with connected to the motor.
Hello, I'm Hishamuddin, and now I will continue about the result and discussion for the design PMDC motor. Firstly, we will see the result and we discuss about the low power motor first. As you can see, this is the figure for the quadrant 1. The following blue waveform represent the speed and the torque of the motor, while the following yellow waveform is represent the reference input signal of the speed and the torque. In quadrant 1, the PMDC motor operates in a forward motoring. As the torque were required in order to rotate the motor, the torque obtained in the figure is positive as the speed of the motor. Armature current remain constant and directly proportional to the torque of the motor. So the speed of the motor remain constant while the torque becomes zero. So this figure explains both the speed and torque of the motor in quadrant 2. The PMDC motor operating in forward braking region within this quadrant. Torque of the motor breaks the reverse rotation of the motor before the reversing motor mode begins. At t equal to 20 seconds, the torque becomes negative in order to change the direction of the motor while the speed of the motor decreases due to the reference input signal. Next, we go to the quadrant 3, a forward reversing which results in both the motor and the torque moving in the same direction, but both in negative state. Similar to that in quadrant 1, the torque is required to rotate the motor but in different regions, showing the reversing effect. Lastly, we go to the quadrant 4. The result obtained shows both the torque of the motor is positive while the speed of the motor is in negative. The torque required to rotate the motor in reverse direction. Now we move into the medium power motor. The figure shows the speed, torque and armature current graph for the PMDC motor which operates in quadrant 1. The blue waveform refers to the speed of motor, while the yellow waveform refers to the speed of torque at graph time against speed. For the graph time against torque, the blue waveform and yellow waveform have changed to torque. For the following time against armature current graph, the pink waveform referring to the armature current. In this quadrant, the PMDC motor operates in forward motoring. Since the torque were required in order to rotate the motor, the torque obtained is positive as the speed of the motor. Also, the blue waveform is the speed and the torque of the motor, while the yellow waveform shows the reference input signal of the speed and the torque. Armature current remains constant, directly proportional to the torque of the motor. The speed of the motor remains constant while the torque becomes zero. This figure expresses the speed, torque and armature current graph for the PMDC motor operating in quadrant 2. In this quadrant, PMDC operates in forward braking. Torque of the motor breaks the reverse rotation of the motor before the begins of reversing motor mode. The speed graph expresses the same as quadrant 1, but with a slight difference. When t equals 20 seconds, the torque becomes negative as a requirement for the change in direction of the motor. The speed of the motor and the armature current have decreased significantly. In quadrant 3, PMDC we operating in forward reversing. The speed, torque and armature current graph show the graph is inverse for the quadrant 1. The torque is required to rotate the motor but in different region which is reversing. The armature current is inverse from the quadrant 1. The last quadrant is quadrant 4. In this figure, the graph shows the speed of the motor is negative, while the torque of the motor is positive. The torque required to rotate the motor in inverse direction. The armature current is inverse from the stated at the quadrant 2. The controller performance for both speed and torque were analyzed by using Bob plot. The performance analysis is conducted using magnetic simulating to verify that the values for PI controllers for speed and torque are compatible to get the desired output. Based on the parameters for the low-power DC motor models, the verification for both the speed and torque controller design are shown via simulation using Bob plot. The values of PI controller for torque control loop is determined by calculating the values. The cross frequency is chosen approximately to order of magnitude smaller than the switching frequency of the converter. Therefore, the values of omega, KIT, and KPT are 3141.6 radian per second, 239.2939, and 2.9859 respectively. Based on the simulation result, we express the controller design for torque reach stability. The bandwidth obtained is larger, which is 3141 radian per second with a phase margin of 90 degrees. As for the speed controller design, its cross frequency chosen were approximately 4 orders of magnitude smaller than that of the torque loop. Therefore, the values of omega, Ki omega, and Kp omega are 0.3142 radian per second, 0.001 and 0.1885 respectively. Following the simulation result in figure, it shows that the controller design for speed also reached its stability. The bandwidth obtained which is 0.314 radian per second with phase margin of 89 degrees. We express the performance of both speed and torque controller for the low power DC motor, give the fast response, minimum overshoot, and given zero steady state error, saying the values of bandwidth are large with the values for phase margin are over 65 degrees. Based on the parameter of medium power DC motor model, the cross frequency is chosen approximate by 2 orders of magnitude smaller than of the switching frequency for the converters. Therefore, the values of omega CT, KIT, and KPT are 3141.6 radian per second, 74.3484, and 0.8586 respectively. As shown by the simulation result in figure, the bandwidth obtained is indeed large, which is 3141 radian per second with a phase margin of 90 degrees. As for the speed controller design, the cross frequency chosen is approximated by 4 orders of magnitude smaller than of the torque loop. Therefore, the values of omega C omega, Ki omega, and Kp omega are 0.13142 radian per second, 0.0015, and 0.2677 respectively. Following the simulation result shown by the figure, the bandwidth obtained is 0.314 radian per second, while the phase margin is 89 degrees. It indicates the performance of both the speed and torque controller for the mid-power DC motor indeed give a fast response with minimal overshoot and zero steady state error, since the value of bandwidth are large and the value of phase margin are larger than 65 degrees. As a conclusion, based on the simulation of the design, a conclusion can be made from the result where it shows the operational DC motor in all 4 quadrants, both forwards and reverse operational. The result has also been discussed in terms of both torque and speed, while the PI controller has been used in order to tune in the parameter for the DC motor. The Bob plot has also been analyzed in order to get the better performance of torque and speed controller. The objective of the assignment is indeed successfully achieved, and the operation of quadrant DC motor in all four quadrants managed to be controlled by varying the two levels of power rating, which are low and medium power rating. So that's all for us. Thank you so much.